whenever we have a service that finishes and there is more than one job waiting in the queue, the system must decide which will be the next one that will be served, okay? We can have different selection policy, okay? Those selection policy, each one, even the one that seems to be less useful, might have a specific scenario where they can work better than another, okay? So let's see which are the type of policy to decide which will be the next job that will enter service as soon as a job leaves and we have to select which will be the next one entering the service. Okay, first of all, this queuing policy, how we call these selection criteria, can be divided into big macro categories. We have non-preemptive policies and preemptive policies, okay? In non-preemptive policies, if one job is started, it cannot be interrupted. So whenever we start one job, it will always be completed from start to finish without interruption, which was one of the hypotheses that we have kept until now. However, there is also another hypothesis, which is quite common, that are preemptive policies. So, policies where, for some reason, the job which is currently in service might be stopped and resumed later, okay? So, there could be some event at which, at the time when that event will occur, we will stop the job in service and we will start another one. Actually, in what we have described until now, we actually had one cases where we were talking about this opportunity of stopping one job and continuing it later, okay? I will return on that example later. Okay, so let's focus on non-preemptive policies. There are a lot of them, but let's say that the 5 policy that we might be interested in considering when jobs cannot be interrupted are the most obvious: first come, first served, job served in order of arrival, the one that we have supposed up to now, last in, first out, last come, first served, so the opposite. When one job finishes, I will not serve the first, I will serve the last which arrived. Service in random order, I don't have any order, I randomly pick something up. Things like shortest job first or longest job first, okay? These are 5 policies that are quite usual whenever we specify the policy. Remember, these are things that also belong to the Kendall notation. So we can have something like MG1 SJF. Okay, this could be a way of denoting one system where jobs arrives according to a Poisson process after exponential inter-arrival time, are served according to a general distribution. We have one server, and jobs are served in this shortest job first policy. Okay, so the first one, the first come first served is, or first in first out, is the simplest one. Jobs arrives and basically they are served in order. So the first jobs that arrives is job A. Job A starts in service immediately. Then just after job A, we have that arrives in almost a burst job B, C, and D. So job B starts only when job A is finished. Job C starts only when job B is finished, and job D starts only when job C is finished. Jobs are served in order of arrival. Okay. Last come first served has two versions, the preemptive one and the non-preemptive one. The non-preemptive one basically stores the jobs in that arrive and serve them from the last one which arrived in the queue on. This is something that, even if won't seem to be fair, as a matter of fact, can be very useful when what you are serving are not people or are not things that a user would like to be done first, but are things that are just tools that actually nobody cares about. Think, for example, when you have the plates where you eat, it is much easier to stack the plates one on top of the other and then get the new one from the top of the stack. Okay? There are many cases in which if you stack the things one on top of the other, it's much easier to get the one on the top rather than get the first that you put there. If are things like plate, where as long as they are clean and not broken, any plate would be good for putting your meat on top of it. The last come first served might simplify the process of putting the clean plate and get the one where you put the food, because it's much easier. You don't have to lift and remove the one that arrived later or put them in some sort of vertical position which we do not know, they might fall, etc., etc. So there are plenty of scenarios where last come first served could be better, because it will be much simpler to implement and there might not be things where we actually really care. Okay, so here, since from the beginning of A, the last to arrive was job D, as soon as job A finishes, the next one to start will be job D. Then, since things are served in inverse order of arrival, since D we had that job C was arrived, so next we'll start job C, etc., etc. Okay. Please note that should we had anything arrived here, job E arrived when, for example, job D was served, this job E would have passed in front of job C, because each time the last one arrived, the top of the stack will always be the one that will be taken for service. Okay? And I repeat, this is an extremely useful policy whenever you have things that actually don't care when they have done. Okay. Service in random order, instead, once a job finishes, you pick up randomly any between the ones that were already there in the queue. Okay? So, you pick any randomly. So, for example, here after A, the random choice took job C, then to pick a random choice between B and D, it picked B, and then finally there was just job D, and that passed. Okay? Big question. Which one of the three is the one that gives the best response time? How many vote for first come, first served? How many vote for service in random order? How many vote for last come, first served? How many doesn't want to vote? Okay. Actually, the question, it has been proved that all the non-preemptive policies that performs a choice without knowing the length of the jobs have exactly the same average response time. So, the average time one job will have to stay in the system, both in the first come, first served and in the last come, first served, will have the same average time. Okay? It will be the same. So, actually, this works as good as the first come, first served. They have the same average service time. So, why most of the time you are not happy if things are served in last come, first served, but you are more happy if you are served in first come, first served? There is for sure. There must be some difference between the two. Okay? The difference comes from the variance, because the variability of the response time of the first come first served is much less than the variability of the service in random order, and it is much less than the variability of the last come first served. Variability because here in first come first served, more or less all the jobs will be served about the same time. Last come first served, there will be the lucky guys who arrive late, and since they arrive late, they will be served first, and the poor guys that were the first to arrive and will have to wait forever for their turn. Okay? This will be well balanced because the average will be the same, because we will have a lot of latecomer lucky guys and a few poor women that arrived in the beginning and had to wait the whole day. Okay? So actually, things goes at the variance level. What happens instead in the shortest job first? So, if, which is something that is actually not the case, you can know in advance the service time of one job. For example, you are downloading a file, most probably a short file will take a shorter time than a longer file. When you are passing the cart at the supermarket, probably a cart that has just a piece of bread and some towel will be much faster than what have a full cart for 1 week of food for a family of 5 persons. Okay, you might understand who is shorter and which is longer. Sometimes you can know the service time required to complete the job in advance. In that case, you might order the jobs in the queue according to their service time and pick up the jobs to do the shortest job first. Okay? It can be proven that choosing the shortest job first can provide an extremely small average service time. Similarly works the longest job first, where instead you pick up the longest jobs at the beginning and then you leave the shortest jobs later. Okay? So here in this table I have considered a system where we have an exponential service time of an average of 800 milliseconds and an inter-arrival times of 1 second. So the system is stable with a utilization of 80%, and I have computed which is the average queue length. You see, the average number of jobs in the system will always be 4. For first come first served, last come first served, and service in random order. Okay? Shortest job first will be much faster because being able to choose the jobs, letting the short job pass first will reduce the average waiting time of everybody, while the longest job first will increase the average waiting time of most of the job. Look instead at the variance. First come first served has a very limited variance, so around 16. The last come first served has a much higher variance, almost 10 times, and the service in random order has also a slightly larger variance. Okay? By changing the discipline, it is true that first come first served and last come first served has the same average service time, but the variability will be enormous because in last come first served, some poor job will have to wait an eternity, while most of the lucky one will pass very quickly. Okay, so last come first served is a very good policy, except for the few bad lucky guys that will have to wait for an eternity. Okay, and service in random order, sometimes it's better, sometimes it's more. It depends all on the luck. So if you have bad luck, you will have to wait an eternity, that's why it has a larger variance, okay? And whenever you can choose at the job, choosing the shortest first will reduce the waiting time of everybody, so it will decrease the average service time, while making the long job pass first will increase the waiting time of everybody and will increase the average response time. Okay? Okay, so this is all about non-preemptive queuing policy. What about preemptive policies? Preemptive policies are instead policy where once a job finishes, we select the next one. We can interrupt one job before it finishes. Okay, there are many. The four it is important to present are the last come first served preemptive, round robin. Please try not to confuse this with the routing. Let's move to round robin. Round robin was the only preemptive policy that we have mentioned in some of the previous examples. In particular, we mentioned this policy when we were considering the state machine of the operative system. Okay, when we were considering the state machine of the operative system, we had something where we have two jobs that alternate in execution, okay? That was an example of round-robin policy. In round-robin policy, each job has assigned a quantum of time. If it can finish before that quantum of time is okay, otherwise, if it cannot finish in that quantum of time, another job is executed. The job is stopped, another one is executed, another one is executed, until we have executed everything else, and then we return to this job, okay? Keep in mind that this is the typical scheduling policy used in operative system. Every operative system, Linux, Windows, etc., to allow to run multitasking, so concurrently run many processes at the same time, uses this type of round-robin policy. The only difference are how big is the quantum. In most of the cases, the quantum will not be fixed, but it will be variable, and which will be the order after which one job will be re-put in service and when the other will do. It is pretty interesting to see policy like the perfectly fair scheduler or something like that, I don't remember the name, of Linux, which have very clever way of deciding the length of the quantum and the order in which a quantum is assigned to each of the processes to make sure that the shortest job will end first, but also the longest one won't starve waiting for the CPU. Okay? So this is one reason. Round robin is very used because probably this is the way in which operative system works, and whenever we have several tasks run in an operative system in parallel, most of the time this will be the policy. However, implementing this is extremely complex. Analytically, due to the fact that we have to consider this quantum of time, but also if we would like to make an event-based simulation like the state machine that we did before, there will be a lot of changes of states to consider the process. So it will be extremely hard and difficult to simulate. For this reason, it was invented a special policy which is called processor sharing. That is a very clever approximation of the round robin that occurs when the quantum of time tends to zero. If the quantum of time tends to 0, all the processes have an extremely small amount of time that is executed in parallel, one after the other, okay? So imagine that this became very, very small, so all the processes are basically executed in parallel, okay? But of course, there is just one process. So the way in which the round-robin work, the processor sharing work, is this one. If there is just one job, it gets the full processing speed. So if the jobs will take 1 minute, it will run in 1 minute. If there are 2 jobs, the processor sharing will equally divide the server between the 2. So if one job individually would have taken 1 minute, when we have 2 jobs, it will take 2 minutes because it will be using the CPU only half of the time. When there are 3 jobs, each one will receive 1/3 of the service. When we have 4 jobs, each one will run in parallel at 1/4 of the speed. Okay? Since we are running at 1/4 of the speed, there will be one moment in which one of the jobs will finish. Probably here, job A will finish. Because it was the first being started, and here all the jobs have exactly the same amount of time, so more or less at this point of time, job A will finish. Then we will have that 3 jobs remain, so the 3 jobs will start being executed slightly faster until the second job, job B, will finish. Then we will have only 2 jobs remaining, which will be served now much faster, since each one will have half of the CPU. When also the 3rd job finishes, the last job will have the CPU all by itself and will be run. This is the perfect policy to simulate CPU in multitasking execution environment, but also network. If we have several transfers going on in our computer, the total completion time of the job will be this one. We all know that if we are downloading one movie, it might take some minutes. If you are downloading 4 movies at the same time, most probably each of these movies will take 4 times for being completed because the bandwidth will be shared between the processes, okay? So, this is very important, and even if having this quantum that tends to 0 is quite hard, since it is some sort of theoretical framework, this is extremely easy to model, and there are a lot of analytical results that will consider this type of policy, okay? So, even if not, while the round robin is something that has an aspect in reality, this is an abstraction of what happens in reality, which, however, is very close. Just note at the difference between arrival and service curves that we know is what really defines the service time. Between this, the round robin, and the processor sharing. You see, they are very, very similar. If you look at this area and this area, they are very, very similar. Because processor sharing, it is a good approximation of round robin.